The year was 1962. Across America, the horsepower war was escalating into something close to an arms race. Every major manufacturer seemed obsessed with one idea: bigger engines, bigger displacement, bigger pistons, bigger power. If you wanted to win races, dominate drag strips, or impress buyers in a dealership showroom, the formula seemed simple. Add cubic inches. Dealerships plastered numbers across their windows: 389, 406, 409. The bigger the number, the more attention it commanded. Salesmen didn't need to explain compression ratios or valve timing. They just pointed to the displacement figure and watched customers nod in approval. But inside Chevrolet, a small group of engineers had a different idea. What if a small block could embarrass engines nearly twice its size? What if precision could beat brute force? What if the entire industry was thinking about performance the wrong way? And what happened next would create one of the most legendary engines in American history: the Chevy 327 Fuelie, an engine so advanced for its time that it shocked racers, terrified competitors, and proved that cubic inches weren't everything. Most people know the myth, but almost nobody knows the real story, because the 327 Fuelie wasn't supposed to dominate. It was supposed to be impossible. To understand why, you have to go back to the late 1950s. At the time, Chevrolet's small block V8 was already becoming a legend. Introduced in 1955 as a compact 265 cubic inch engine, it had evolved rapidly. Engineers led by Ed Cole understood something many competitors didn't. Weight mattered. A lighter engine improved handling, acceleration, braking, and reliability. Instead of simply building massive V8s, Chevrolet focused on creating efficient power. Ed Cole was a visionary who believed in elegance over excess. He pushed his team to think differently, to design smarter, to build engines that worked with the car instead of simply overpowering it. That philosophy was radical in an era when most manufacturers measured success strictly in displacement. Cole had joined Chevrolet in 1952 and immediately began reshaping the division's approach to performance. He believed that a well-designed small engine could outperform a poorly designed large one. His team focused on minimizing weight while maximizing strength. They studied airflow patterns, they tested different bore and stroke combinations. They obsessed over details that other manufacturers ignored. The original 265 small block weighed just 530 pounds. Compare that to many competitor engines that tip the scales at 650 pounds or more. That weight savings translated directly into better performance across every metric. By 1962, the small block family had grown into something special. The new 327 cubic inch version combined a 4.00-inch bore with a 3.25-inch stroke. That might sound like a simple specification, but it created a powerful combination. The large bore allowed bigger valves and improved airflow. The shorter stroke reduced piston speed and made high RPM operations safer. Engineers called it over-square design. The bore was larger than the stroke. That relationship fundamentally changed how the engine breathed. Larger bores meant more room for valve area. More valve area meant better flow. Better flow meant more power at higher RPM. It was a completely different approach than what most American manufacturers were pursuing. Ford, Chrysler, and others often used longer strokes to increase displacement. That created good low-end torque but limited high RPM capability. Chevrolet went the opposite direction. The result was an engine that loved to rev, and Chevrolet was about to take that concept much further. Because there was a problem. Ford was getting faster. Chrysler was getting more aggressive. Pontiac was building increasingly powerful V8s, and racing success sold cars. Every Monday morning, customers walked into dealerships asking about the cars they'd seen win on Sunday. Racing created brand loyalty. It influenced purchasing decisions. It made reputations. Chevrolet needed something extraordinary, something nobody expected, something that would make headlines and change perceptions. Something that would prove their engineering philosophy was correct. The answer came from a technology many manufacturers had already abandoned: fuel injection. Today, fuel injection is normal. Every modern car uses it. In 1962, It felt like science fiction. Most drivers had never seen it, most mechanics didn't understand it, and most manufacturers had tried it and given up. Chrysler experimented with it briefly in the 1950s. Their Bendix system appeared on some 300 models, but was plagued with problems. The technology wasn't reliable enough. Manufacturing tolerances weren't tight enough. Service support wasn't adequate. Pontiac attempted their own version. Both abandoned the technology after encountering complexity and reliability issues. The systems were expensive to produce, difficult to calibrate, and required precision that manufacturing tolerances of the era struggled to maintain consistently. Every component had to be machined to exact specifications. Any variation affected performance. Fuel pressure had to be precisely controlled. Air metering had to be accurate. Temperature compensation had to work flawlessly. It was asking a lot from 1960s technology, but Chevrolet persisted. They worked with Rochester to develop a mechanical fuel injection system that could actually survive in production vehicles. The Rochester system was a masterpiece of mechanical engineering. Complex, yes. Temperamental, absolutely. But when properly set up, it was extraordinary. Chevrolet's Rochester mechanical fuel injection system replaced the traditional carburetor with a sophisticated setup capable of delivering fuel with remarkable precision. The system wasn't cheap, it wasn't simple, and mechanics often hated it, but when it worked, it transformed the engine. The system used a complex arrangement of mechanical linkages, a fuel meter, and individual fuel lines to each cylinder. There was no electronic control, no sensors, no computers. Everything was mechanical. Springs, diaphragms, and precisely machined components worked together to measure airflow and deliver exactly the right amount of fuel. A large air meter sat atop the engine, measuring incoming air. Mechanical linkages translated that airflow into fuel delivery rates. The fuel distributor then sent precisely metered fuel to each cylinder through individual lines. It was engineering at its finest and its most fragile. The tolerances were incredibly tight. Components had to be manufactured with precision that was unusual for automotive parts of that era. Assembly required care and expertise. Adjustment required knowledge that most mechanics simply didn't possess. The highest performance version of the 327 became known simply as the Fuelie. Officially rated at 360 horsepower at 6,000 revolutions per minute and approximately 352 lb-ft of torque, it achieved something extraordinary. 1 horsepower per cubic inch. That number sounds ordinary today. Back then, it was revolutionary. For American production engines, 1 horsepower per cubic inch was considered a magical benchmark. European exotics sometimes achieved it. Ferrari's V12 engines reached it. Race engines occasionally exceeded it. But American street engines, almost never. The big American V8s made torque. They made reliability. They made power at low RPM. But they rarely made 1 horsepower per cubic inch in street-legal trim. Chevrolet had reached it without superchargers, without turbochargers, just engineering, pure, intelligent, relentless engineering, and the specifications were impressive. The Fuelie used an aggressive solid-lifter camshaft, high-flow cylinder heads, larger valves, and an 11.25:1 compression ratio. The camshaft was a Duntov design, named after Zora Arkus Duntov, Chevrolet's legendary engineer. The profile was aggressive with significant overlap and high lift. The solid lifters eliminated the cushioning effect of hydraulic designs, allowing more precise valve control at high RPM. That compression ratio was extremely high for a street engine of the era. Most passenger cars ran compression ratios between 8.5:1 and 10:1. The Fuelie pushed well beyond that. Higher compression meant more power, but it also meant more stress, more heat, more demand on every component. Pistons had to withstand higher pressures, rings had to seal perfectly, head gaskets had to survive extreme conditions. Premium fuel wasn't optional. It was mandatory. Run regular gas and the engine would knock itself to pieces. Literally, detonation would destroy pistons, burn valves, crack heads. The fuel requirements were serious and non-negotiable, but drivers didn't care because the performance was breathtaking. Road tests routinely recorded quarter-mile times in the low 14-second range. Some skilled drivers pushed properly tuned Fuelie Corvettes into the high 13s. Top speeds exceeded 140 miles per hour. In the early 1960s, that was serious territory. The kind of speed that got attention, the kind of speed that won races, the kind of speed that created legends. Contemporary road testers describe the acceleration as violent, intoxicating. Unlike anything else available in American showrooms, Car and Driver tested a Fuelie Corvette and called it one of the fastest American cars they'd ever driven. Motor Trend praised the instant throttle response. Road and Track, usually critical of American cars, admitted the Fuelie was genuinely impressive, but Chevrolet engineers weren't celebrating yet. Because building power is one thing, keeping it alive is another. And then the real challenge began. Mechanical fuel injection was incredibly sensitive. Temperature changes affected tuning. Altitude changes affected performance. Humidity could alter the air-fuel mixture. Improper adjustments could make the engine run poorly, or even damage components. Drive from sea level to the mountains, and the mixture would go rich. The air meter couldn't automatically compensate like modern systems. Drive on a cold morning after tuning on a hot afternoon, and the engine would run differently. Many dealership mechanics lacked experience with the system. The technology was too new, too complex, too different from everything they'd learned. Carburetors were familiar. Mechanics understood jets, floats, accelerator pumps, and chokes. Fuel injection was foreign territory. The service manuals tried to explain it, but reading about it and actually working on it were very different experiences. Owners would bring their cars in complaining about rough, idle, or drivability issues. Sometimes the mechanics made things worse. They'd adjust linkages without understanding the relationships, change settings that shouldn't be changed, force components that needed gentle precision, turn adjustment screws randomly hoping to fix problems. Former Chevrolet engineers later recalled that diagnosing Fuelie systems required patience and expertise that many shops simply didn't possess. One mechanic reportedly joked, "Half the problems weren't in the injection system, they were caused by mechanics trying to fix the injection system." Service bulletins tried to help. Training programs were organized, special tools were developed, but the learning curve remained steep. Some owners became experts themselves. They learned to adjust their own systems. They understood how temperature affected the mixture. They knew which adjustments did what. These owners loved their Fuelies and wouldn't trade them for anything. Others grew frustrated and had the fuel injection removed, replacing it with a carburetor, yet racers loved it because at full throttle, everything made sense. The Fuelie delivered razor-sharp throttle response, no hesitation, no lag, no carburetor bog, just immediate acceleration. Press the pedal, and the engine responded instantly, like flipping a switch. Carburetors had inherent delays. The accelerator pump had to squirt fuel. The venturi had to create vacuum. Airflow had to stabilize. Fuel injection bypassed all that. It delivered fuel directly and immediately. The difference could be felt instantly. Drivers who experienced both systems never wanted to go back. Carburetors felt sluggish by comparison, imprecise. The Fuelie spoiled people, and competitors noticed. At drag strips across America, smaller 327 powered cars were humiliating larger displacement rivals. Think about that for a moment. Big block engines often carried 389, 406, 413, or even more cubic inches. Pontiac's 389, Ford's 406, Chrysler's 413 wedge, Oldsmobile's 394, massive engines built for brute force. Yet this little 327 kept showing up and ruining people's weekends. Why? Wait, the small block was significantly lighter than many competing engines, sometimes by over 100 pounds. In some cases, nearly 150 pounds lighter than the biggest competitors. Less weight over the front axle improved traction and balance. The cars launched harder. Weight transfer to the rear wheels was better. The front end didn't lift as much. Traction was improved. The cars changed direction faster. They felt more nimble, more responsive, stopped faster. Less mass meant shorter braking distances, and often reached the finish line first. Weight distribution made a bigger difference than most people realized. A lighter nose meant less transfer to the rear during acceleration. Better balance meant improved cornering. The whole car worked better. Handling, braking, acceleration, everything improved. Most people don't realize how important that advantage was. Power matters, but power-to-weight ratio wins races. And the 327 Fuelie understood that better than almost anything else on the road. Still, Chevrolet wasn't finished. As racers pushed the engines harder, weaknesses began to appear. Valve float became a concern at extreme RPM. The factory valve springs couldn't always control the valves beyond certain engine speeds. Past 6,500 revolutions per minute, some racers reported float. The valves couldn't follow the cam lobe properly. Solid lifter adjustments required regular maintenance, every few thousand miles, sometimes more often under racing conditions. The lash had to be checked and reset periodically. It was a time-consuming process, but absolutely necessary for reliability. Ignition systems struggled to keep up with increasingly aggressive tuning. Points-type distributors had limitations at high RPM. The spark would scatter, timing would wander, performance suffered, the points would bounce, dwell would change, spark energy would decrease. Some racers reported worn valvetrain components after repeated high RPM abuse. Rocker arms would wear, pushrods would bend, valve tips would mushroom, cam lobes would show wear. Others discovered limitations in factory exhaust systems. The restrictive manifolds choked power, the small diameter pipes created back pressure, horsepower was left on the table, significant horsepower in some cases. The fixes came quickly: stronger valve springs, improved ignition tuning, better headers, more careful camshaft setups, performance distributors with stronger springs and better advance curves, dual-point systems for more consistent spark, eventually early electronic ignitions. Aftermarket companies jumped on the opportunity. The aftermarket embraced the 327 almost immediately. Companies saw the potential. They developed parts specifically for the platform. High-performance camshafts with profiles designed for fuel injection, lightweight valve train components that reduced inertia, improved rocker arm designs with better geometry, stronger pushrods, better valve springs. And suddenly, the horsepower numbers started climbing. Officially, Chevrolet claimed 360 horsepower. In race trim, many builders extracted 400 horsepower or more. Some heavily modified examples approached 450. A few pushed even higher. With the right combination of parts, 475 horsepower was achievable, in an engine weighing substantially less than many big block competitors. That was a terrifying combination, and then racing proved it. Throughout the early and mid-1960s, Corvettes equipped with Fuelie engines became formidable competitors in SCCA racing. Drivers pushed the cars hard through corners where heavier competitors struggled. The small block's balance gave it an advantage that raw horsepower couldn't always overcome. At tracks across America, the pattern repeated itself. A larger engine would dominate the straightaways. The big Fords and Chryslers would pull away. Their displacement advantage showed. Then the Fuelie Corvette would claw back time in the corners, braking later, carrying more speed through the turns, accelerating earlier on exit, lap after lap, race after race. The engineering philosophy was working. Names like Dr. Dick Thompson and Don Yanko became synonymous with Fuelie's success. They understood the engine, respected its capabilities, and drove it to victories that shocked competitors. Dr. Stower, Dick Thompson, known as the Flying Dentist, became particularly famous for extracting every bit of performance from Fuelie Corvettes. But perhaps the most important victory wasn't a trophy. It was perception. The Fuelie changed how enthusiasts thought about performance. For decades, many buyers believed displacement was everything. More cubic inches automatically meant more speed. Bigger was always better. The 327 challenged that assumption. Suddenly, enthusiasts were discussing airflow, compression, volumetric efficiency, cylinder head design, RPM capability, cam timing, valve events, breathing characteristics. The conversation became more sophisticated. Magazine articles went deeper into technical details. Enthusiasts learned the vocabulary of performance. They understood that a well-designed small engine could beat a poorly designed large one, and Chevrolet benefited enormously. Because the company had proven that smart engineering could outperform brute force, that thinking differently could create advantages, that innovation mattered as much as displacement. But there was another problem coming, one that no engineer could solve. The market was changing. By the mid-1960s, larger engines were becoming increasingly popular. The muscle car era was beginning. Customers loved big numbers. 396 cubic inches sounded more impressive than 327. 454 sounded incredible. Dealerships loved easy sales. A big number on the fender sold cars. No explanation needed. No technical discussion required. And manufacturers discovered that adding displacement often required less explanation than promoting advanced technology. Mechanical fuel injection also remained expensive. The option added significant cost to an already expensive car. Several $100s in 1960s money, a carburetor was cheaper, simpler. For many buyers, the performance difference wasn't worth the additional cost, especially when carbureted engines were becoming more powerful. Holley 4 barrels were getting better. Tuning was improving. The gap was narrowing. A well-tuned carburetor could get close to fuel injection performance. Close enough for most buyers. Fuel injection gradually lost favor. Sales numbers declined year after year. Fewer and fewer customers checked the fuel injection option box. The final Fuelie Corvette rolled off the line in 1965. After that, Chevrolet shifted toward high-performance carbureted combinations, big Holley carbs, tunnel ram intakes, multiple carburetor setups. The era of the factory Fuelie was ending, but the legend was just beginning, because collectors quickly recognized what these cars represented. They weren't simply powerful, they were milestones, engineering achievements, turning points in automotive history. The Fuelie marked the moment American manufacturers proved that sophisticated engineering could compete with sheer displacement. Today, original Fuelie Corvettes command enormous prices. Rare, documented examples often sell for well into six figures. The most desirable cars can exceed that by a substantial margin. Perfectly restored 1963 Fuelie Corvettes have sold for over $500,000. Split-window coupes with fuel injection bring even more. And the reason goes beyond rarity. Collectors understand what they're buying. They're buying a turning point. They're buying an engineering statement. They're buying proof that innovation can beat convention. They're buying the car that changed the conversation. Even modern engine designers still follow principles demonstrated by the 327 Fuelie decades ago. Efficient airflow, high RPM breathing, precise fuel delivery, optimized combustion. Those ideas remain fundamental today. The technology has changed. Electronic fuel injection replaced mechanical systems. Computer control replaced mechanical linkages, but the philosophy hasn't changed. Precision matters, efficiency matters, smart engineering matters, and that's what makes this story so remarkable. The 327 Fuelie wasn't the biggest engine of its era. It wasn't the most powerful engine ever built. It wasn't even the easiest engine to own. But it changed the conversation. It proved that intelligence could beat size, that efficiency could beat excess, and that a small block could humble giants. In its most famous form, the Fuelie produced 360 horsepower from 327 cubic inches using a 4.00-inch bore, 3.25-inch stroke, and an astonishing 11.25:1 compression ratio. It became one of the first American production engines to achieve the magical 1 horsepower per cubic inch milestone and helped redefine what performance meant in the 1960s. More than 60 years later, enthusiasts still talk about it. Not because it was the biggest, but because it didn't need to be. The Chevy 327 Fuelie proved that sometimes the smartest engine in the room is also the fastest, and that's why its legend refuses to die. If you enjoyed this story, let me know in the comments what legendary engine you'd like to see next. There are still plenty of forgotten masterpieces, engineering battles, and racing legends waiting to be uncovered. And make sure to subscribe so you don't miss the next deep dive into the machines that changed automotive history forever.